Welcome back to the Math Professors. If you enjoy content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Ben Hamlin, and I'm going to cover stochastic matrices today. Which really is an application of matrix multiplication, and this is kind of mixed with maybe a probability course and how matrices can be used to determine customers after so many years. So here's how it goes. I have two cable companies that are competing for customers in a city of, say, 100,000. Company A has 30,000 and Company B has 50,000 customers, and the remaining have no service. So I'm going to assume the probability of switching from one company to the other. So we're going to keep track of, how many people in A are going to go to B, how many A are going to go to no service, similar with B, and then also similar with no service. And we're going to have like a little graph down here kind of showing, the probability of everybody switching from one to the other. So I can see the probability of switching from company A to B is 20%, from A to no service is 10%. Similarly, company B to A is 30%, and from B to no service is 10%. And also we're going to assume the probability of the person with no service is switching to A is 25%, or to B is 35%. Eventually we're going to ask, after we set this up, after 1 year, what are the customers going to look like? Maybe after 2 years, after 5 years, how would we do that? And eventually, is there a steady state? After so many years, is it basically going to be the same amount in every single pot, every pot, essentially? So let's create a little picture here. So what I have is I'm going to have company A, we're going to have company B, and we're going to have our no service. And I'm just going to keep track of where everybody goes. So from from A to B, it's 20%. So from this to this, we know this is going to be equal to 0.2. It also says from A to no service is going to be 10%. So this is going to be 10%. Now, that's only 30% of the customers, going from A to another one, which means that 70% are staying with this company. So 0.7. Now, very similarly, when we're talking about company B, switching from company B to company A is going to be 30%. So going from B back to A is going to be 30%. And then it also says from B to no service is going to be 10%. So it's going to be 0.10. I guess I don't need the zeros there. Now, again, how many people are leaving B? So if I have 40% leaving B, then I'm going to have 60% remaining. And then finally, our no service. So people with no service switching to A is 25%. So no service to A is going to be 0.25. And also no service to B is going to be 35%. So this is 0.35. And then finally, what's leaving? We have 0.25 and also 0.35. So we're going to have 40% saying. Make sure that that's right. 30, yep, 40% saying. So 0.4. Now, I said this is about stochastic matrices, and what we're going to do is we're going to build one, and they have particular properties. So when we build this, I'm going to have, this is going to be company A, this is going to be company B, and this is going to be the no service company. And this is going to be our from side. And over here, I'm going to have the exact same order. This is going to be A, this is going to be B, and this is going to be no service. And this is going to be our to side. So what I'm going to do is I'm going to build a matrix here, and we're just going to keep track of these probabilities. So we know from A to A, you can see that's this 0.7. Now from B to A, so from, actually we'll just go all the way down A. So from A to B, so A to B is going to be 0.2. And finally, from A to no service is going to be equal to 0.1. Now working with B. From B to A is 0.3. From B to B is 0.6. And finally, from B to no is going to be 0.1 again. All right, so now from no service to A is going to be 0.25. Now, no service to B is going to be 0.35. And finally, no service to itself is going to be equal to 0.4. Now, what makes this a stochastic matrix is all entries or all elements are between 0 and 1, which really kind of represent probabilities. And it also has like kind of the probability distribution requirement that the sum of the probabilities has to equal 1. So you can see that this column is equal to 1. Same thing for B, all the probabilities, the sum of all the probabilities is also equal to 1. And same thing, the sum of all the probabilities of no service is also equal to 1. So this is a stochastic matrix, and we usually label this label P. It really is because it has to do with probabilities. Now we're going to have our other matrix, which is going to be matrix X, and this is going to be our population. Where is everybody in the beginning? Well, it says company A has 30,000, so I'm going to have it in the same order as this. So we're going to have, an A, we're going to have a B, and we're going to have a no. So company A has 30,000. It says company B has 50,000. And then, of course, we have a total of 100,000 people. So if that's 80,000, the known have 20,000. And that right there is our matrix X. So if I want to know, say, for the very first one, it says, what about after 1 year? So if I want to determine what are the people after a single year, well, I'll just call this thing A. So after 1 year, this is just going to be equal to matrix P times matrix X. So we can multiply these things together, 0.7, 0.3, 0.25, 0.2, 0.6, 0.35, 0.1, 0.1, 0.4, and then multiplying by our population at this particular time, 30,000, 50,000, and then 20,000. Now, in the previous video, I showed you how to do multiplication by hand. So, it's just going to be 0.7 times 30 plus 0.3 times 50,000. So 0.7 times 37 plus 0.3 times 50,000 times 0.25 times 20,000. And let's do that real quick by hand. I'm going to find that first entry. And I'm going to talk about how we do this just, by using matrix multiplication maybe in a calculator. So 0.7 times 30,000 plus 0.3 times 50,000 plus 0.25 times 20,000. Enter. So what I get for this is going to be 41,000. Now it's very similar for the second row, except it's going to be 0.2 times the top, 0.6, 0.35. So 0.2 times 30,000 plus 0.6 times 50,000 plus 0.35 times 20,000. This gives us 43,000. And what you'll notice is this, remember the sum is going to have to equal 100,000. So this number is already kind of predetermined here. So what do we have? We have 84,000, so this better be 16,000. So let's check. 0.1 times 30,000 plus 0.1 times 50,000 plus 0.4 times 20,000. And there we have 16,000. Now I was going to say another way to do this is, we can do this by hand in our calculator, or we can hit the matrix button. So second, and then right below the math, you see the inverse button. So second, hit that inverse button, and that's matrices. And I'm going to go over and I'm going to hit edit, and this right here is a 3x3 matrix. So edit and go 3, enter, 3, enter, and that puts 3x3 on top. And then type in the numbers, 0.7 equal, 0.3 equal, 0.25, enter, 0.2, enter, 0.6, enter, 0.35, enter. So we're just typing this matrix in. Then we make sure that we got it right, 0.7, 0.2, 0.1, 0.3, 0.6, 0.1, 0.25, 0.35, 0.4. Beautiful. There's our P matrix. Now, second quit. We're going to go back into that matrix because you have to edit it, because if you try to do stuff, you're going to be in that last entry. So we hit second quit to get back to your home page. And you go second matrix, and we're going to go back to edit, but we're going to edit B. So I'm going to let this thing be matrix B. And this is a 3x1, so 30,000, 50,000, 20,000. Okay, now second quit again. I don't want to do stuff inside the entry, so second matrix, we're going to go A, times second matrix, we're going to go B, and then boom, it gives us that matrix right there. Now, if I want to find after, say, 2 years, B. After 2 years, remember, this is after a year, so what you would do is you just do matrix P times, that previous matrix. But remember, that previous matrix is Px, so this is going to be P times Px. And since multiplication is associative, I can just go P times Px, which is equal to P squared x. So, I can multiply this by P again, and it's going to give you the exact same thing as I do here. So that's actually a little bit easier. So what I'm going to do is I'll go insert, and I'm going to square that matrix. So P squared x is going to give me 4, 5, 6, 0, 0. So that's company A. Company B is going to be 39,600. And finally, no service is going to have 14,800 people. So again, this is how many are company A. This is going to be in B, and this is going to be no service after 1 year. And very similar. This is A, this is B, and this is no service after 2 years. After 5 years, that power just becomes a 5. So I'm going to change that power to a 5. So let's say C, after 5 years, we're going to have P to the 5th x is going to be equal to, it's round. I'm not going to round, but we'll talk about what the answer a book would likely want, or like what makes sense to us. Because this happens, and what we know is this represents customers at a particular time, and we know we can't have these 0.6s, so, or 0.8s or 0.6s. So you're gonna have to we basically round them. But you can see company A, company B, company C. Now, what's kind of interesting here is as these powers get higher. So let's say D. How about after like 10 years, P10x? What would that look like? A second there. So let's change this to a 10. So after 10 years, I would get 48807 point. It says 26877. I'm just going to go 3. And then 36906.98. Ooh, 98. Well, I'll go 98 then, I guess. If I'm going to do that, I'm going to do this as 2627. And then 14285.75. And I've rounded those. I'm sure they go on a while. And then let's go after, I don't know, let's go 50 years. What the heck's going to happen after 50 years? Well, after 50 years, run out of room. So E, what about after 50 years? P50x. So this is going to equal 48809.52, 36904.76, and then 14285.71. And I'm going to put 99 in here. 99, because that's, I don't know if it's going to overflow on me. But when you plug in 99, I get exactly the same thing here. So what happens is, over time, this thing is going to reach a steady state that over so many years, this is how many is going to be in A, this is how many is going to be in B, and this is how many is going to be in C. And it's not going to change for those particular companies from year to year to year. That's assuming all these probabilities are the same. Which is likely why you see a bunch of advertising dollars go into these companies, so they can actually change this and not have to worry about a steady state and possibly get higher numbers. So if you like the content, please subscribe.